First, the modulus operator is distributive. This means that y times r mod x is equal to y mod x times r mod x. Secondly, if y mod x is equal to r, then y plus 1 mod x is equal to r plus 1. Same thing with multiplication. If y mod x is equal to r, then y times z mod x is equal to r times z. Next, you can perform a specific type of modulus division if you're dealing with a prime value for x. If y times z mod x is equal to r, then z is equal to r minus y times z mod x. You can solve for y or z by adding x to both sides without changing the equation. Using these facts, we can prove then for y times z mod p is equal to plus or minus 1. If we set y is equal to 6, then 6 times z mod p is equal to plus or minus 1. Then z is always equal to plus or minus p plus 1 over 6 mod p. Next, we can reduce the integers to the twin prime number line like this: 1a, 1b, 2a, 2b, etc., where a's and b's are the location for all the possible twin primes, which are either x mod 6 is equal to 1, which we would count as a b, or x mod 6 is equal to 5, which we would count as an a. Then we can combine all the a's and b's together to get that 1 is equal to 6. 2 is equal to 12, 3 is equal to 18, and really what we mean by 1 is equal to 6, we mean that 1 is equal to 5 and 7, 2 is equal to 11 and 13, etc. We can now state that the number 1 will not have a twin prime in relation to the prime 5 if plus or minus p plus 1 over 6 mod 5 does not equal 1. In other words, for p is equal to 5, if 1 is not congruent to either 5 plus 1 over 6 mod 5 or 5 plus 1 over 6 negative mod 5, which we can then evaluate to be x mod 5 is equal to 1 or 4, then 1 is still possibly twin prime. Otherwise, it must be divisible by x. However, the congruence relationship does not apply for the first p plus 1 over 6, which we can prove. Thus, in accordance to the prime 5, since the first twin prime is not congruent to either x mod 5 is equal to 1 or 4, then the first twin prime may still be prime in relation to 5. Or another way to say that is 5 does not divide either 5 or 7. Now 5 does divide 5, but that's also why you need to ignore the first output of p plus 1 over 6, because the first output is related to the prime itself. We can then do the exact same process to check 2, 3, and then get to 4. 4 mod 5 is in the congruence class negative p plus 1 over 6 mod 5, which is equal to 4. Thus, the fourth possible twin prime, or 4 times 6 is equal to 24, must not be twin prime, because either 24 minus 1 or 24 plus 1 is divisible by 5. We can repeat the exact same process with every type of prime. And then notice that through this redefinition, there is a one-to-one relationship between the integers being reduced to the primes as between the integers being reduced to the twin primes. Next, we prove if we apply a modular condition onto the integers, for instance, the prime's modular condition is that if x mod p is equal to 0, then it is not a prime, otherwise it still can be, that such a modular condition does not affect the infinitude of any other x mod p is equal to n. In other words, if we strike out all x mod p sub 1 is equal to z, then we proved that for q mod p2 is equal to r, they will still be infinite, despite having crossed out that other set of numbers. And this is true no matter what value you choose for p1, p2, x, q, r, and z. Thus, if we choose to reduce the integers by x mod p is equal to p plus 1 over 6 and z mod p is equal to negative p plus 1 over 6 instead of x mod p is equal to 0, we have therefore proven that this would still result in an infinite set of numbers. But the twin primes are this exact reduction, except framed from the perspective of multiples of 6. Therefore, since there are obviously infinite multiples of 6, we have proven the twin prime conjecture.